Okay, so today we're going to talk about support vector machines, which is a kind of ML model which can be used for either classification or regression. This topic would be focusing on classification, how this can be used as a classifier. And kernelization is an important topic because it talks about how you can, if the data is non-linearly separable, right? So it's the first time we're going to learn about non-linear decision boundaries. So kernelization is basically a technique where you try to create a classifier or a model in a high dimensional space where the data set can be linearly separable, right? So in the original dimensions or feature space, it's non-linear in terms of decision boundaries, but at higher dimensional spaces, it can be converted to a linear model. So that's what the topic today is all about. So I've used these slides, which I feel have done a great job in terms of explaining the concepts. So I would be like editing these slides while I'm teaching. So let me know if you have any queries. So, so just to recap what the binary classification was all about, like on the left-hand side, you have a kind of a linearly separable data, right? And on the right-hand side is kind of a non-linearly separable data. As you can see that if it's a feature 1 and feature 2, you can think of it as x1 or x2, right? So here you kind of know that they can be a linear classifier. But in this case, you know, in a non-linear decision boundary, you might get a idea that this might be kind of a non-linear decision boundary, right? So in a kind of binary classification, you want to classify data sets into class 1 or class 2. So let's say class 1 is called as +1 and the class 2 is called as -1. So based on what the value or evaluation of your classifier is on a given test sample, right? If it is greater than equal to 0, you assign it to positive class. If it is less than equal to 0, you assign it to negative class. So a way to write this in a compact notation is, you can think of it like this, right? If you take the product of the label, so if in your training data set, right, if you take the product of the true label and the evaluation of that function, right, if the signs of these are same, right, if you evaluate it to be plus class, positive class, and if your label is also positive, right, that means you correctly classified it, right? If your prediction was negative class and the true label was also negative, so this product would again be positive, right? And if it is not positive, if the evaluation of this product happens to be negative, that means that it's a misclassification, right? So this equation or the model that we want to learn can be thought of it like this, right? So that's what the idea was all about, that in the first row here, these are all examples of linearly separable data. Suppose you want to distinguish between blue circles and red triangles, right? So if the data is arranged like this, it's a vertical classifier. Then if the data is arranged like the second one here, right, I'm going to number these so that it's easy for you to follow, right? In the second plot, it's like a slant line, but it's still a linear decision boundary, right? In this topic, we'll also look into data which are non-linearly separable. So for example, in plot 3, it happens to be linear in terms of looking at the model, but you can see there's a small triangle which is in between the circle, right? So we are going to talk about, do you want to learn these complex decision boundaries where you would want to classify accurately, or you think that this might be a kind of an outlier? So for better generalization, I can still consider it to be a linear model, right? So this is the kind of decision we have to make, that do you want to learn a non-linear decision boundary on plot 3, or you are still good with using a linear decision boundary, but then you take some misclassifications into your account, right? So this might be a good way of generalizing. Whereas this earlier example was more of overfitting, right? So this is overfitting. We're going to go in details, but I'm going to motivate this using some plots here. Again, in this fourth example, now for all matters and purposes, you can still fit a linear model. But then the accuracy, the validation accuracy, the test accuracy, the training accuracy would be quite bad, right? So while in this case, in orange plot, your training error is exactly 0. Whereas in this vertical linear line, training error is kind of not completely 0, but at least your validation error would be good. That means it's good it has a good generalization. In plot 4, you can still learn a linear decision boundary, but the training error would be quite high. That means you are underfitting the model. So in this case, an ideal scenario would be that I might want to learn a non-linear decision space like this, where everything on one side of this curve is one class, on the outside of this decision boundary is another class. Now to do this in this feature space x1 comma x2, right? This is kind of tricky to learn a non-linear decision boundaries. So that's where we will use kernelization to transform this non-linear data set into a linearly separable data set in some high dimension. And in the hope that at this high dimension, it kind of becomes linearly separable. Just to give you a quick motivation, think of this 2D plane that you have in plot 4, just raise that blue circles on the top. Like just raise those blue circles on the top into the 3D space. So your triangles still lie on the plane, whereas your blue circles are now hanging in the air. So between your between your screen and the points which are above it, you can have a hyperplane which divides these two or classifies these two into two different categories. So if you take this to a 3D representation, you can learn a linear classifier, right? So that is the whole idea of kernelization. So linear classifiers have been we have learned that this can be modeled as W transpose X plus D. So in this case, W would be D cross 1 vector. X is, I'm going to write it as an arrow here, which basically means a vector. So this is a D-dimensional vector as well, right? For any input sample, W transpose X would be a scalar quantity, and you're adding a kind of another parameter, which is P, right? So what we can think of it as is this linearly separable decision boundary is where Fx is equal to 0. That means it's an equation of a plane. So you can think of it as an equation of a line in 2D space, which is x1 cross x2, or in high dimensional space, you can think of it as an equation of a plane, right? So in a d-dimensional space, it would be a hyperplane, right? So in that case, all the points which might lie on this vertical line, right, which is this linear line, all those points would satisfy this equation because they are satisfying the plane. They are on this plane, right? Everything on the left hand side, for example, can be considered to be less than equal to 0. Everything on the right hand side is considered to be greater than 0. And how do you know that? Probably this is the origin. If you know that if you put the point origin into that equation, if it evaluates to be negative, then every point which is on this side would be a negative class, right? And everything on that other side would be a positive class, right? So that's what this kind of equation is. So W basically in terms of geometry from class 11th or 12th, right? Just to remind you guys that W is basically normal to the line or normal to the plane, right? It's called a weight vector in this case model, but in terms of geometry, it's basically normal to the plane. So if you have a plane, hyperplane, then W is the normal vector to the plane, right? Whereas X would be some point on this plane. So that's how an equation of a plane can be written down. So that's what the example of equation of a plane was, like in a 3-dimensional space. Now that equation of a line becomes equation of a plane, right? So in a n-dimensional data, it can become an n-dimensional plane, right? So one key thing to note, probably you might have learned KNN classifier previously, nearest neighbors, right? So just keep in mind that in KNN, while you would want to store all the training data even after learning the model, because based on the training data, you classify which of the K classes it is closest to. But in terms of these linear classifier models, what we're going to talk about, we just learn W and then we discard the training data, right? Now, everything now depends on how this function fx evaluates on a given test sample. And only information you need to have is W and B, which are the parameters. So you don't care about the training data. So only W is needed for classifying new data. And you can think of it as B as well, right? Any questions so far? That this is important to understand this equation, the 3D plane, and what we're trying to do. And it's still a linear decision boundary. I'll pause for quick questions if you have. Are there any? I will just quickly look. Hand raised. Okay, great. So everyone is following, right? So we talked about a perceptron classifier last time, which has this equation, which is again a linear model. And the whole idea was about, for every one input sample, your W can be updated, right? So in that case, if so this is basically sign of your model. So if you are misclassifying a positive sample, right? If you're misclassifying a positive sample, that means incorrectly you classified plus as negative. So you need to then increase your W. So in that case, the sign would be positive. If you are a negative sample, true negative sample, but the prediction was positive, right? That means you need to then decrease your W update. So that was taught last time. So in summary, this is what was happening, right? So you can see that these updates, this sign can be negative or positive based on if you misclassify a positive sample or negative sample. So the way the perceptron is different from what we're going to learn today, SVM, is in perceptron, it's a kind of an online update. You can do an online update, right? But the fact is here that every point is trying to influence the decision boundary, right? So tomorrow, if you bring in a new training data set or add new training samples, now that points would also start influencing and readjusting this line, right? Whereas what we're going to learn in support vector machines is basically you have the entire training sample all at once, and then you find out which is the best line in terms of classifying these 2 points. And we'll define the notion of what a best classifier means. What is the best fit criteria? For example, we learned in regression that the best fit criteria was least square estimation, right? Least squares fit, like reducing the MSE. In this, so that was the objective in linear regression, that fit a model so that your MSE is low, mean square error. So we want to understand that what we are trying to optimize in SVMs, right? So as you can see here, like there are like plots of circles and crosses. So perceptron example, the perceptron model can learn this classifier, right, that we have on the screen. Now you can see here that this classifier is closely cutting across some of these points, right? If you have these points, that means it's as tight as possible to the decisions or boundaries of these two sides, right? If this is side 1, class 1, this is class -1, right? The two classes, it is right at the, like, just cutting across. That means a slight deviation from this line, you start misclassifying the test samples. So what we would want is, this model might not be good for generalization because you never know what your test sample is, right? Your test sample, if it slightly lies near this plane, it might start influencing the decision boundary as well, because it might not generalize well, right? Because you have to take into account what if there's some outlier in your data set and all that, right? So what we were hoping is, we are trying to study a model like SVM, where for the first time I'm trying to introduce this term where we are talking about intuition is we are going to prefer a larger margin. That means please give me some space around this line so that in future I can have some test points here and there, but I still do a good generalization on the testing samples. You can't be too strict. So this is like too strict for me, right? So this is too strict. It's just cutting cross, right? So we need a kind of a larger margin. We need a kind of a free space around this line where we can be relaxed, right? We can say, oh, it's fine if we have some space here where I don't have to worry a lot, right, in terms of classification. So we're going to define what this means. So to have that intuition, let's go over this plot, right? So out of these 4 plots, 1, 2, 3, 4. Now, we have not taught you anything yet, right? Just from your visual inspection or intuition, what do you think? Which of these 4 classifiers do you think is basically a good classifier that can work well on generalization, that can work well on unseen test sample? Well, that's right. 4 is a good fit, right? In this case, it's not good because it's misclassifying a lot of samples. In this case, it is too close to blue. This one is kind of nice. It is nice. Training error is 0. So you can be happy that training error is 0. Here, training error is not 0. Here, training error is 0. But this is poor generalization. It's too much bias towards this side, right? This one is nice. Third one is nice. Probably perceptron might learn this 3. But the thing is, it can have a good training error, like 0 training error, but poor generalization. A small blue dot somewhere here might be misclassified as triangle. But in reality, it might just be an outlier and it should have been classified as blue class. So we say 4 is a good fit. Now, how do you think 4 is a good fit? What prompted you to think 4 is a good fit? Can you just quickly write down like 2-3 words, what prompted you that 4 is a good fit and not 3? So now I'm talking about 3 versus 4. Well, that's right. So Ashish, so yes, so, yeah, exactly. So you are giving kind of some free space around this line where you're trying to say that within this point. So basically what we're trying to do is we're trying to maximize the distance between these 2 classes, right? So it's basically trying to say we're trying to maximize the margin, right? So this should be my scope. So that means anything beyond this is for triangle, and anything on the left of this is now this one. So we are no longer concerned about this vertical line, which is the equation of that classifier. For us, decision would be easy if we can find out these dashed or dotted lines, where we can guarantee that anything which is on the right hand side of this dotted line is basically triangle class. Anything on the left hand side of this is a blue class. So that is our goal. So I hope everybody is fine with this. If there are any questions, let me know. This is our goal. And this is all coming from intuition. Maximizing the margin. Okay, great. So that's what it was, right? Maximizing the margin solution because it's more stable under some perturbations of the inputs, right? Because you do have to take into account that inputs can have some kind of outliers here and there, right? So that brings us to what support vector machines is. Like one of my favorite models from classical ML, right, is SVM. My research also, I've published some papers on SVM. So the good thing about SVM is it's all geometry. Like if you can understand the geometrical significance of everything, you understand SVM. It's less to do on maths and more to do on geometry and visualizing, right? So I probably might cover this entire lecture just throwing in these geometrical significances, and mathematical equations are just a way of representing that geometrical abstract. right? So hopefully you might have revised some of the maths concepts. If not, go back home and revise. Okay. So things we would probably need is equation of a plane, right? So there was this pre-quiz we had designed, but I think we were late in terms of publishing it. So we'll publish it after this lecture. So there the questions would be on equation of a plane, right? What is the distance of a point from a plane? What is the distance of an origin from a plane? So those are the questions that we have in pre-quizzes, and that's what all we need. So I might probably give you some of those answers right here while discussing, because that's how the lecture is. Like, it's before the quiz now. So think of it like, now discard this part at the bottom, right? Don't worry about that expression, right? Just think of it, this middle line is W transpose X plus B equal to 0. So let's consider this as an equation of a line or equation of a plane, right? For me, it's easier to consider it as an equation of a plane because I know we rarely work in a two-dimensional space. So it is an equation of a plane where W is D cross 1 and X is a D cross 1 vector. That means every point is plotted on this graph. What we, Aryan, what if we have some points in the boundary? Well, here is an example where the points are on the boundary. They have a special name in SVM. So we'll talk all about that, right? So what we have here is we have this red and blue class, right? And we're trying to find out that, okay, who are your front line? So this is all about linear classifiers for the time being, right? So we're trying to talk to this blue class and saying, okay, who are your frontline warriors, right? So I'm saying, oh, I'm the front line, I'm the front line. You talk to the red class and tell them, okay, who is your frontline data points, who are closest to your blue points. Okay, you said this one and this one, right? And then we say, oh, okay, if you two are the candidates who are very closest to red family, and if you, so let's say 1, 2, 3, 4. So these 4 points are closest to each other's boundaries, right? So we say that, okay, let's just draw a line or a plane which goes over 1 and 2. Let's draw a line or a plane which goes over these 3 and 4. And then simply take a plane which bisects this space. So this is bisecting. Why? Because this distance is same as this distance from this plane, right? So we have 2 parallel lines. So we try to fit 2 parallel lines, blue and so this one and this one. And basically the intuition is the bisector of that plane is basically what we have as the actual decision equation of the decision plane, right? Question. Okay, I'll pause here now. So just let me just wrap up quickly before I take the question. I just want to cover all the geometry that you see here. Okay, let me just do that. So here is the deal, right? If W transpose X plus B is an equation of a plane, what is the distance of the origin from this plane? So first of all, you have to find out what is the distance of any point Z from this plane. Well, from geometry, it is basically W transpose Z plus B it's like this, right? So a quick example, AX plus BY equal to C, right? So that means A Z1 plus B Z2 minus C by A square plus B square under root. So in school, we have learned more of this kind of structure, which is same as in kind of matrix vector notation. This is what we have. So if you want to find out distance of an origin from that plane, so now Z is 0. So in that case, what you have is this, assuming B is positive, right? Or you can think of it magnitude of B, but we'll say B is positive for the time being. So that is the distance of origin from that decision surface. Just so now these frontline warriors are something called as support vectors. And the intuition is support vector basically means these are the points on which the decision boundary would be supported. Because as I told you that these points, support vectors, are influencing what these margins are. And then the bisector of that is actually the decision boundary. So basically, if you can find the support vectors, you can find the decision boundary. Or if you have a decision boundary, then you know that it has been supported on some support on some of the data points, which are called as support vectors. Right? That's where the name comes from. Now, open to questions. So first of all, I will go to raise hand because I think Kasina had a query up front. Go ahead, Kasina.
Yeah, JD. So you said, like, see these two blue points which are there on the border. How do you identify those 2 points? I mean to
That
say,
is the
see,
entire game of optimization. That's what the entire
no, no, just a minute.
why will it
So,
call why will it be called as a learning algorithm? That is the entire
yeah, no,
learning.
no. What I mean to say is, you said after you find the blue line and the red line, that is when you find the bisector of these two lines, and that you fix it up as the
Where
uh, what do we say, the
the
classifier,
decision plane.
right? Yeah,
Yeah.
the decision plane, right? So what I'm asking is that to decide those two are the points on the border, you have to always measure the distance of those
Mm,
points with respect to something, right? What is that?
exactly.
What
Uh,
is that
well,
something that you're measuring it with respect to?
right. So what I'm trying to show here is just an intuition of where the support vector name is coming from. But the notion of that distance that you're talking about, that margin. So
Yeah.
what you see here is D and D. So basically, you have to maximize 2D. Do you agree?
Yes.
I'm going to define what D is in terms of W transpose X plus B. If I can maximize 2D, I would know I would have a kind of a separating plane, right?
Yeah.
So I'm going to define that. I'm just giving you an intuition that what this line is, why is it at exactly at the middle of these two lines, right? I'm
Okay.
just giving you intuition.
Okay.
But the whole idea is I'm going just everyone just keep an eye on this term. Maximizing 2D, twice of the distance. Okay. Asina, let's wait for some more slides to come up, and probably if you still have questions, let me know.
Yeah, sure.
Right? Okay, great. Thank you.
Shall we go over some chat questions?
Yes, I'm now going to the chat question. Satyajit, it is far from, okay, that was space margin. Okay, Aryan, what if we have some points in the boundary? We have some points in the boundary, those are called the support vectors, right? And then we will see cases where points can now be within the margin as well. We are not saying that margin is a space where there is no data sample. In this example, where you have a perfectly linear classifier, there is nothing in between. This is basically called as, let me throw in another term, hard margin. Hard margin is strict, probably like your nursery teacher or somebody like in class 5 or 6, right? Like hard margin is very strict, which basically says I'm not going to take any point in between the margin. It's very strict. And let me tell you, this might actually lead you to think that this is actually a kind of strict model, might be poor in generalization if you're too strict. Just we'll come to all these concepts, but if it's coming from intuition, great. Next question. How do we fit the parallel line? Well, unfortunately, not all points are in 2D space, so we can't use our geometry, like direct geometry formulas. But how do we fit the parallel line is basically what our optimization goal would be. How to come up with these lines, right? How to come up with this W transpose X plus B. See, the whole idea is W and B. If I can find a W and B, which is the bisector of this space, then I'm good. So basically, maximizing 2D, that objective is same as find that golden W and B, which is right at the bisection of these two planes. is the same thing. Maximize 2D or find that W comma B, which is at the bisection of those two margins, which is same as optimization goal, find the support vectors. All these are equivalent problems. If you can't see that, do let me know right now. All these are equivalent problems. Maximizing the margin distance, or finding that sweet W and B which bisects the plane, or find those support vectors. If you can do any of these three, you can find all the other features. So if you have to find the distance between two planes, you can find that 2D. If you want to find the line, W comma B. If you want to find the support vectors, so all these three are interrelated. If you have one, you can find other two. Will the line from origin be a normal? Oh, we are concerned about. So distance is always perpendicular distance, right? Because you have to find the shortest. What is the distance? Euclidean distance is the shortest distance between a point and a line or a plane, right? So it would be vertical to this plane, right? And that's what these are. This distance is all vertical distances, distance between two parallel lines. That's the whole idea. So this is, there can be a lot of distances, but the fact we decide as distances is the shortest distance, right? Which is would be vertical to the plane. I hope that answers your query. Saurabh, Gaurav, what is the intuition behind the distance from origin? No. So I just wanted to bring in this flavor of what this B by W is, right? It is the distance from origin to this plane. Okay, let me tell you this. Origin is an easy point, right? I just wanted to motivate what a distance from origin to a plane was. Generally speaking, generalized is this one. W transpose Z plus B, where Z is any point in the space, right? So we'll talk about that. We will use this formula to calculate this twice of D, if that helps. Okay, any questions on the YouTube?
Not really.
Okay, great. Everyone is understanding. Nice. So we talked about this fact that we want to calculate 2D, right? Okay. Maybe let's try to define. Okay, this I will come to this. Okay, let's really jump on this part, right? Now, what I'm trying to say here is, now ignore everything at the top, right? There might be important, but just let me drive this through intuition. You have this W transpose X plus B equal to 0, which is the black line, right? That is the equation of the plane that you want to learn. Now, let's say everything on this side is plus and this is negative class, right? So we can say that if there are any blue points sitting here, which are the frontline warriors, right? If that helps you to understand, like line of defense, right? So let me draw it with a red line. So these are the support vectors, because I know beyond this there is no point yet, and behind all these frontline defense you have the entire family of -1 class. Beyond this frontline defense of blue, you have everything of +1 family, so they are guarding those, right? Okay, yeah, that's great. So in that case, what we can see here is this line, blue line, would have a form W transpose X plus B equal to 1, right? So we can hope that, let's try to learn a line for which W transpose X for all the positive classes is equal to +1, and W transpose X for all the samples which have a negative class plus B is equal to -1. So because right now these are parallel planes. How do you know these are parallel planes? Look at W. If you look at W, the three W's are same. That means all of them are sharing the same normal. So they are parallel to each other, right? So the only difference is it B equal to +1? Is it like B? So if you have to reword this is basically B -1, right? W transpose X plus B -1 equal to 0. This one, red one, is W transpose X plus B plus 1 equal to 0, right? So what has happened is this notion of B has changed. On the right hand side, I have zeros. I've just reworded that equation, and that's what we have, right? Now let's come back to what the distance between 2 points in the plane is, right? Now, what you can think of is you have a point here. I'll come back to the questions. Please be patient if there are any questions in the chat coming up. So these support vectors, let's call it as x plus, and it's called as x minus, right? So that means suppose we take this point, which is x plus, right? Let me keep it still blue, right? This is my, let's say, x plus, any x plus, and this is my x minus, right? So x plus, so this distance is basically the vector. So this is basically this vector. Any point on that blue line from any point on that red line. Now, how do I find a distance between these two lines, right? This, it's all geometry. This is the x plus minus xy, it's slant. The distance between two lines is basically this green line. I want to know what this green line is. That is the actual distance, the shortest distance, which is perpendicular to both planes. Well, if you know that this is actually, if you have a perpendicular to these planes, it is characterized by W, which is the normal, right? Yeah, if you want to draw it like this, it's fine. If you want to draw it upwards, basically I want to say that perpendicular to this plane is basically characterized by W, right? So if you find the projection of this arrow line along, if this is your x plus minus x vector, and if you find the projection, let's say it's called W, right? Let's say it's pointing this side. So we need to find this one, projection of this line on W, which is basically a dot product. So what you see here is, can anyone tell me what does this mean? W by magnitude of W. Try to recall 11. Not or
Unit vector.
Direction
unit
of W.
vector. Unit vector. Excellent. So it's basically the unit vector for the normal, right? Unit normal. So in this case, the magnitude is 1. So basically what we're trying to say is the projection of x plus minus x minus on unit vector along the normal, right? Which is the dot product. Now that dot product, you know, is basically W transpose something, right? Because you do a element by element dot product and add, it has the same effect as this W transpose x plus minus x minus by x W. Let me know if this is not clear, right? Because this is just same as doing a dot product, but in a vectorized notation. Now let's try to see what this is. If you are, try to, like, when you're listening these lectures, try to have a copy and a pen on the side, because it's easy for you to understand while I'm speaking but not doing anything, right? So try to derive everything back home, right? A W transpose x plus is what? It's the equation here, right? It's a plus family. That is equal to 1 minus B from this equation at the top. W transpose x minus is basically minus 1 minus B, right? What is this formula telling me? It is telling me subtract W transpose x plus from minus W transpose x minus. So I'm going to subtract these two quantities. 1 minus B minus 1 minus B, which basically would give me 1 minus B plus 1 plus, what happened? Plus 1 plus B, right? Minus B gets cancelled. 1 plus 1 is 2. So the numerator is 2. Denominator is the normalization constant. What have I found out? Kasina, have I found out 2D? Everyone who are curious about this part. 2D, right? What is that 2D? Twice of what is my goal? Maximizing 2D, maximizing the margin. This is my goal. If it's not clear here, take a minute or two to go over this derivation and convince yourself, or if it makes sense, I have started to write down what my actual objective is, maximizing the margin. Open to questions now. Well, on the chat first. Divya, our goal is to find the support vectors first or the center line. Well, it's like a chicken or egg problem. I'm going to approach it as finding the maximum margin. And intuition is that is going to lead me to that sweet W and B, which probably also will let me know what the dual is. So, I threw in this word. Support vectors is something which can be found from an alternate optimization form, which is called as dual problem. Okay, now that I have uttered it, there is something called as primal and dual. These are the different forms of optimization problem. So this is in terms of W, this is called a primal form. Dual form is an alternative of this primal form. But here we are going to learn, objective is to find those support vectors. So finding support vectors, optimizing for support vectors in the dual problem is same as finding the maximum margin in the primal problem. So finding maximum margin probably will give you W because it's optimizing on W, which is equivalent to finding support vectors in the dual problem. And we'll see more about that because that's better when we talk about kernelizations. Okay, question. Oh, okay, there is a chat. Maximizing 2 by norm W is equivalent to minimizing W. Well, Harshit, you are 1 or 2 slides ahead, right? So exactly, we will come to that. Okay, I just want to bring in some geometry and convince you that what we are trying to do. Questions on raise hand. Ram Mohan.
Could you please again explain the one? Where did the one come from? WTX plus B equal to 1 for the margin.
Well, for me, the intuition was about this class, right? So what I wanted to have is I wanted to have a line. So this was all positive classes on this side. And Dr. Sethi, please feel free to add more or correct me because that's what my interpretation is. So if you have a positive samples on this side, right? So I want a line where on putting positive samples, I get my decision as +1 because the whole idea is what? Either you are +1 family or -1 family. So if I put in X from this side of the graph, my decision is +1. That means it's a +1 family. If I'm on the bottom part of this graph, if I put in any point from this, ideally this point is on the right hand side of this black line. So it should be negative class. So if I put in any X minus, or X minus basically means points belonging to negative family. So points belonging to negative family, if I put in this equation of line, W transpose X plus B, which is basically your middle line, right? Equal to 0.
Yeah.
So either this formula should give you +1 or -1 based on decision, right?
Yeah, no, yeah, I got that part. So what I'm trying to say is, what I'm trying to understand is, let's say these 4 points, 2 blue points and 2 red points, if they were in practicality, they can be a little bit far away also. So even in that case, would the constant not change? Would it still remain +1? I'm finding that hard to understand.
Yeah, they would be still. It would still be +1, right? Because if they are farther from here, and if you see, suppose these points are shifted, right? Suppose I shifted by zooming in, right? For example, I zoom in, but then there can if there are any points which are within this, right? So now those won't be the support vectors. right? These two new points, if there happen to be points closer to the other side of the territory, those would be now the support vectors, right? So those would probably have W transpose X plus B equal to 1. So this is all about how you are defining your positive and negative classes. That plane. And you in reality, you do not know these points, right? Because these are in a higher dimensional space. So your estimation is anything which is on this side of the plane, anything on this side is positive, anything on this side is negative. And are they satisfying this equation of the line? Well, yes. If it is a positive sample, this would evaluate 2 plus 1, which means it's on that side of the boundary. Dr. Sethi, do you have anything to add or clarify more? Okay, probably he might not be there right now. Okay, first of all, let's go to Ram Mohan. He has his hand raised.
I just asked the question. Thank
you.
Oh,
can you have your? Yeah, thank you.
Yeah,
thank you. Gauranga? Gauranga, go ahead.
My question is the blue line that is the connecting line of the support vectors, that is blue line and the red line, are they parallel? I think they should not be parallel. Are they parallel?
Yes. We have to find margins which is like parallel margin in a linearly classified data. No, so this is all linear classifiers. Just be careful on that. I can have points like this in a curve, right? Now in that case, this is my decision boundary and this is my margin, right? But what we do is we don't learn it in this space. We will take it into a higher dimensional where it can be linearly classified, because the whole objective function is based on maximizing the distance, right? So we'll take it to a plane, higher dimensional plane where they can be linearly classified, whose effect on the original plane would be that this is a kind of a curve.
No, my question is, suppose there is 4 point, the line has been made with 4 points, right? Like 2 points for each line. Suppose one line is like distance between one set of red and blue dots are different than another set of red and blue dot. In that case, the line might not be perpendicular. It might be a little bit of diverging.
No, so the whole idea is if you take two sticks, if you take blue stick and a red stick, and if your data set is such that there is a good gap in between, right? So this is like a very linearly separable data set. It's ideal. It's not in reality, it doesn't happen like this, right? Ideally, there is nothing in that white space between blue and red. If you take these two sticks, you're trying to find out which are the closest line of defenses for both the armies, right? And then you try to stick this line. It can happen that it goes like this and it goes like this. So the whole idea is to find that. See, the whole idea is we have to find the bisector, right? In a way, we are trying to find the bisector of the space.
Suppose the shape is not like a pipe, it may be like a conical kind of shape. Even in that case also we can get the bisector of it, like middle line symmetrically cutting that region of margin. But in that case, it won't be like a parallel blue and red line. It will be a little bit of straight line, but diverging kind of thing.
Like the example I showed at the bottom here?
No, not that one. I am saying the pipe, if the one side of the pipe is wider than the on another side.
Oh, no. You can't have that. Then that means your support vectors, your decision is getting biased towards one class. The whole idea of it's like a LOC, line of control. It is like exactly at the middle, giving equal probability on both the sides. If you shift, if you do not decide it to be exactly as the bisector, then you are favoring one class.
I am saying I am talking about that red line and blue line. If if suppose consider it as a pipe, if one side of the pipe is wider than another side of the pipe, then like it's kind of a bell-shaped kind of case. Even in that case also we can get an line that is actually equidistant from both the line. Can you see the
You're
case?
saying you're saying this example that we drew, a kind of divergent lines or intersecting lines.
Yeah, that one.
No. Then what would happen here? It's a plane, right? What are you trying to do here? Are you trying to exchange the classes after this after this Christmas point? No,
Understood.
right?
Yeah, but I was considering if we do not take that from that crossing point.
Oh, no. This is a plane, right? You know, see, you never know what your test sample can be from, right? Okay, at least that was
Okay,
a good discussion. Yeah, that was a good discussion because that explains why it has to be parallel lines. Yeah, Aryan, thank you for clarification. Vidya, we will surely find red and blue lines, which will be parallel. Well, both the lines are parallel, right? And in reality, we are not finding these lines. I'm just trying to motivate it through geometry that there is a red and a blue line. But in reality, see, I have condensed all that information in this simple form, which is maximizing the margin. And this maximizing the margin basically takes into account there would be some parallel line whose normal vector would be W. And then the distance between two parallel lines whose normal vector is W, and have these equations of plus b equal to 1 plus b equal to minus 1 is basically 2 by norm W. So maximizing this would give me W. It will not give me, like, it will give me some information about W and B, which will help me give this line, which is the actual line. But that intuition, where this intuition came from? No, I was answering.
Hello. Okay,
I was answering Vidya first. Okay. So yeah. Any other follow-up question? I don't see any raised hand. Gauranga, you had any follow-up question?
Yeah.
No.
So,
go ahead.
Yeah. So I am another question is that there is just 1 point for one class, or one point for one class to be the closest to the other class. So in those cases,
Sorry, Gauranga, your voice is breaking. I can't hear anything. The voice is breaking. If you can type it on the chat, if that's better.
Okay, I will type.
Thank you. Aryan, can't we use some other constant other than 1? Well, I'm trying to take constants plus 1 and minus 1 because those are the two classes I'm trying to do. Any class that you have, you can have it as plus 1 or minus 1 because it's symmetrical around 0. That's the whole intuition. That's why here we're not taking as class one class as plus 1, other class as 0. We're trying to be symmetrical here smartly, that a binary classification is label plus 1 or label minus 1. That means it's dogs versus not dogs, right? Cats versus not cats. Plus 1, minus 1. Right. Any other question? Okay. Thank you, Aryan. Any question from YouTube? If any TA is looking at, I don't see. So let's continue.
So there's
right?
a question from YouTube. What if a point falls on the black line?
If a point falls on that black line, right? Well, W transpose X plus B would be equal to 0, right? But do you say this point is a test point or a training point? If it's a training point, probably you might have to optimize your algorithm more so that it doesn't lie there. But if it is a test point, well, then you are in a soup. You really so that's the whole idea, right? You have to find a way that, so see, that is a good question, a really good question, and probably you would want to avoid that by using some kind of, so that's a great question. Why? Because see this one, maximizing 2 by W, it's not taking into account any points which is within the margin. And just hold on to that thought. That is something called as, because this is what, okay, this is called hard margin classifier. Hard margin means do not account for it, do not take any points within those pipe, or what is that gap, right? Basically, I'm going to be very strict. If there are points within the pipe, I'm going to narrow my margin further and further, so that there is absolutely nothing in between those two lines. It's a hard margin. If you have to take into account the point, as you clearly said, there can be data points which can be within the pipe from the test set. That's why we will not try to do hard margin as we go lecture by lecture. We're going to learn a soft margin classifier where it is okay to have red points here. Oops, color. It is okay to have red points here, even though your support vector is here, line. It's okay to have blue points here and there. It's still okay. It's even okay in soft margin to have a misclassified point sitting here. And it's even okay for that soft margin to have misclassified points of blue sitting here, because those can be outliers or something. Like, you don't have to absolutely fit it in the best way. Your best fit criteria is basically to minimize number of misclassifications. So just stick to hard margin for the time being. Soft margin would come later. But I hope all these questions are helpful, but also let's try to see if some of this can be done as more study later, so that can help progress the speed of the lecture as well, because I don't really want to push it to other day. Yeah, avoid overfitting with the excellent. Yeah, that's what the entire intuition is. This hard margin is bad. You can clearly see that it's too ideal a scenario. So we want to avoid all these things. But we are see, we have not even gone to a stage where we are defining the optimization problem yet. That's why your questions are ahead. That's great, but just hold on to that thought. But hopefully these questions help me to quickly go over soft margin, because you already have started developing the intuition. Let's proceed. This is what we had, right? Margin is 2 by norm W. Y equal to +1 family is on upper left. Down bottom is negative class family. For all the points, now here is the equations. The black line, the bisector, it was equal to 0. On that blue point line, we have equal to 1. On the red point line, we have equal to -1. And as you can clearly guess that as I go beyond this, my value after that equal to sign is going to increase. So this is equal to 1. There can be another line which is equation equal to 2. There can be another line whose equation is equal to -2. So on, right? Hence, you can see here that on that space, I have defined what my... So for any point, if it helps, let me do a plus here, because you don't know this plus and minus beforehand. But if it helps, that any point there would have W transpose X plus B greater than 1, because it is beyond the margin. This is beyond the margin. It would be -1, right? So the increase is 0, 1, 0, 1, 2, 3, 0, -1, -2, -3, like that. But we don't care beyond +1, -1, because we know the moment it is greater than 1, it is belonging to plus family as well, right? So these are the critical line of defense, where it is exactly equal to +1. This is the negative line of defense. Consider this army, right? Your civilians are safe. These are your civilians. They are safe. The crucial aspect is the line of defense. Anything breaches that line of defense from other parties, you start to misclassify that point, right? The moment you cross this LOC from this side, you misclassify a point. The moment you start crossing this LOC from top to bottom, you start misclassifying the point. How do we implement this for multi-class then? Well, for me, multi-class is like collection of binary classes, right? A, B, and C, A versus all, B versus all, C versus all, right? So they can think of that as system of binary classifications. But in neural networks, it's much better, right? You can just learn everything in one shot. Or in KNN, you learn everything at one shot. So that's fine. Okay. I hope this is clear, right? Think of it as line of defense civilian if it helps you to understand it. Okay, that brings us to our SVM optimization, maximizing the margin subject to some constraints. Okay, I will come back to some questions after completion of this slide. So I would be strict with you as well a little bit. So maximizing the margin. In the meantime, you can add questions right in the chat. I will look at all at once. So we have to maximize the margin subject to points getting correctly classified. See, what is your constraint? Your constraint is this business of maximizing the margin and the gap around the LOC is good as long as your civilians are safe. That means you have correct civilians on the correct side of the boundary, right? So in that case, for all the data points, you want to ensure that everyone who has citizenship, okay, that can be political, let it be, but if it helps you to understand better, great. If your membership is to this one country plus one, right? If you're a citizen of that country, you should be beyond their line of defense, right? And if you are a citizenship of the other neighboring country, right, you have to be well within the land of that, well within that line of defense of that country, right? So in that way, you can expect that your training error is exactly equal to 0 because you are correctly classifying everything. But that is an ideal scenario, right? Where everybody would be correctly classified. But if it is, for example, in this example, might as well, that is the optimization goal. Maximizing the margin while ensuring there is 0 misclassification. So this is talking about no misclassification. This is hard margin, hard rule. This is a very hard rule, which would learn a hard margin. It's very strict. I'm not going to allow citizens of other countries cross the boundary. So this same problem can be represented as somebody said, maximizing 2 by W is same as minimizing W square because W is a positive quantity. So maximizing this is minimizing the denominator. And then we have already seen it in the first slide, how we can combine this equation into one equation, right? So ultimately, this is my objective for a hard margin classifier. Okay. And this is a quadratic optimization problem because this looks like a norm and all those things, but basically it is W transpose W minimum W. So you can vectorize it subject to, then it can be Y transpose W transpose X plus a column of B can be a column vector now. It is greater than equal to vector of ones. So I've quickly moved it into a matrix domain, right? And then you can use inbuilt QP solver. So it's a quadratic problem because you have a square or a quadratic term. So you can use a standard QP solver from linear algebra. You don't even have to use SVM fit and all those fancy SVM libraries or algorithms. You can directly use a QP solver from linear algebra and give a proper, so QP is like W. So I'm just going to quickly show you that this is W transpose AW plus BW plus C. Minimizing this with respect to some constraints, have a proper QP solver. So in this case, you can think of A as an identity for the time being. It might not be the case, but yeah. So these are the flavors you might actually use as using a quadratic problem, solving it as a QP problem, right? Because even before machine learning, algebra existed, right? So there it is. Okay, so now time for questions. Dibya, who is different from a normal classifier? Who is different? I did not catch the first part. Chinmay, wouldn't this model would have high variance? Oh, low by, yeah, high variance. Sure. It's too strict. When you say high variance, overgeneralization. Ritik Jaiswal. Yeah, high variance means overfitting. Support vector used to minimize over. No. Support vector is not used to minimize overfitting. Support vector are base. Think of support vector as another way of finding that decision plane. I told you those three parts, right? Maximizing the margin is same as equivalent problem. Optimization is finding that W and B of that LOC line, or is same as finding those candidates who would guard the line of defense, which are called the support vectors, on which the entire LOC would depend on, right? So those are the things. Gauranga. Is the support vector only points which have same distance from the decision boundary? No. Support vectors. Well, yeah, like it is a straight line, right? It's again coming back to your question. It's a straight line. There can be even one point on the support vector as well. One support vector on that line as well, right? But then if you have too many samples, probably two. See, we're not going to actually find that line, LOC. So we're actually going to find the LOC. We're not going to actually find the line of defense. See, there is no See, finding that W is same as finding the classifier line, right? And the same as finding those individual line of defenses. Because what is the difference? Plus B equal to 0 versus plus B equal to 1 plus B equal to -1. So it's not a difficult problem. Easy.
We need to find the support vectors, right? For the first, at the first step.
This is an equivalent problem. In primal form, I'm learning W. That was all intuition. And if you have those questions, awesome, because that would probably give you an idea when we go to dual problems, we are learning what those support vectors are.
Okay.
Right? And please go back after this lecture and study because you have great questions, and go over a proper textbook which might reinforce these concepts. I'm trying to get okay. Gauranga, okay, it's done. Shubham, about the issue of constant being 1. Yeah, see, the constant being 1 is just an easy way of saying it's a positive class and a negative class. It's coming from geometry, right? But the whole idea is to maximize that margin 2D, which is now 2 by W. So there is no involvement of B. I chose that smartly so that B and B gets cancelled in the numerator, and you just have 2 upon W. Right? Because you can always argue that I can always argue back saying, why can't we take +1 and -1? Because that will help me remove B from the numerator. If you see that B plus 1 cancelled with B minus 1, and we were only left with 2. Making our jobs easier, right? So Yash, Sanjeev, go ahead.
Yeah, JD, I think, didn't we miss one point over here in the optimization?
I might. Please let me know.
Yeah,
which one?
so W transpose xi plus b has to be greater than equal to 1 or smaller than equal to -1. Along with this, there should be a point on the boundary as well, right? There should be one point for which it is equal to 1 or equal to -1 or something like that.
Well, that is greater than equal to 1, right? That's what it is. There's an equality sign here as well.
What I want to say is, in that case, we are missing the point. What we're missing is, suppose we have a W which does not classify it very good. Okay, like the classification is not too good. But if we scale that W up to some point, then this thing would be satisfied, right? This greater than equal to 1 thing. Do you get my point? Scale both W and B by some constant factor C. Okay. So then this subject to condition would be satisfied, right?
Yeah, it will still be. See, that's what the text I actually didn't want to go through right now. See this one. The derivation actually started from the fact that your C is always in your hand, right? So why not choose +1 and -1, because it's going to be the same planes, right? It's all coming from that. I deliberately left that because I didn't want to confuse a lot of you guys. If it's easier to understand as let's take it +1 and -1 because of the labels, if that helps drive the intuition, because that's what really matters, right? These are all parallel lines. Scaling W will only create another parallel line, right? So I'm just getting, it's just a kind of a technicality, right? Just like you divide by 2 for an optimization problem, so that 2 and 2 gets cancelled. Here I didn't want to have that term be sitting at the top, right? So I made sure that the way I choose these values, I will denote class positive as +1 and -1, so that I have this maximum margin classifier like this.
No, but there is a problem, right? We have created a problem now. So what I'm trying to say is, suppose you have initially you defined it to be 1 or -1, the target values, right? W transpose, when we found this condition that we have to maximize 2 by non-W, that 2 comes off the fact that there were 2 points which were exactly a distance 1 apart, not exactly 1 by non-W apart, right?
Well,
There
because
have-
it's a no, that see, this is also coming from this part. Like if I have to tell you this is 1 upon W and this is also 1 upon W, because it's at the bisection, it becomes 2 upon W. That is the D. The D, which is distance from bisection to one line of difference, is 1 upon W.
Yes, so for these points you would have W transpose xi plus b into y equal to 1, right? Exactly equal to 1.
Yeah.
So you need to have such a point for this optimization to even come into play. Otherwise you won't have that 2 by non-W thing, right? How would you get that 2 by non-W if every point satisfies the condition with greater than 1, right? So for example, every point is 10 apart, distance apart, because non-W is too big
But that
to handle.
But 2 is a constant, right, at the top. Even if you take a line behind this, right, you would have b minus 2, b plus 2 minus of b minus 2, which would again give me some constant at the top. It's to do with W, right? 2 is just a constant. That's what I'm saying. The scaling parameter doesn't depend. Is the numerator a function of W? No, right? You're actually answering your own question. Because that 2 doesn't play any role. Margin, so basically think of it as margin is basically reciprocal of W, inversely convert to norm of W. And that's what my entire hypothesis of optimization is based on. Maximizing the margin. For all that matter, you can disregard that 2. It's not going to affect anything. See, where is 2 here? There is no 2 here. That's what I'm going to play with. Does that mean my optimization is wrong? No. 2 was just a constant.
Okay.
Derivative has to be equal to 0. 2 would be taken equal to 0, thrown out. You will just be solving with W. Okay. Yeah. Good.
I think the answer is in the unit vector thing. We are deriving an unit vector. The length is essentially 1. Right?
Yeah, no, so unit vector is just a direction, right? Ultimately, see, then in this formula, I have to put in this one, right? So his question was, this 1 is coming because we chose that +1 and -1.
Yeah.
But this can be 2 and -2. It would have been 4 upon W. I don't care. 4 upon W. I'm minimizing W, right? See, our goal is not to find the exact margin, right? That margin, again, you said can differentiate based on what scaling parameter you take. Our goal is to minimize W. I think that should convince you. Okay. No questions anywhere. YouTube. Yeah, it comes from proper derivation because I'm taking +1 and -1 as a class, right? It's the margin, 2 upon W, right? And that's how it is modeled as a +1 versus -1. Okay. For any other questions, please, let's go to Campus Wire. I think we have spent a lot of time in tuitions. So as you can see here, that using this is what we would have, right? What we have is 2 classes, blue and red. See, the first one, that is an actual line of difference that you would want to go into. No cross movement across that boundary. 0 training error, perfectly. But that's a very narrow margin, because the margin is not shown here, but margin is distance between 2 closest points from opposite families. So this is the blue line, this is the red. So this is a very narrow margin, right? If I have to draw a narrow tube, right? But again, you can see this is not for good generalization. So what we have is Rather than learning that, we are going to learn this. Simple, easy, one cross movement was allowed. Fine, training error is not exactly equal to 0, but this is much better model because you see the distribution here, see the distribution here. So it's more likely that points on this line would be classified as plus, right? Whereas points here, what if points are here, right? There's a blue point here in this decision that would be classified incorrectly as negative or red label. Whereas the density, according to density, that was right, belonging to the same family of blue, right? So this is a better model. That means we want to cut some slack. We want to cut some slack where we can say that this cross movement is allowed along this LOC as long as you're doing good in terms of unseen points, test points. So a larger margin is what we're trying to look at, right? A large margin solution is better even though one constraint or one data point is violated. So there's always a trade-off between the margin and the number of mistakes on training data. So far, this was zero training loss, right? But now you're trying to think that we might want to trade off between how many points you can allow to misclassify versus the size of the margin, right? Okay. So that's why we have to cut some slack, and that's where the introduction of slack variables come from. Now, against the same plot, but I have made some annotations here. Forget about the text part, just think of the diagrams. So let's find out where my points are. My red point, this red point, 1, I'm calling it as 1. I'm calling this blue point, which is within the margin as 2. Right? And then I'm calling this red point, which is in the other territory as 3. Those are the only 3 points which have been introduced in this example. Now see, if I have to be very strict and very hard, probably I would have learned those dashed lines, red dashed line and the blue dashed line here. But that would have been too narrow a margin to play with, right? So what we have done here is we are trying to find out that what if we take a wider margin, which lets me put these dotted lines at the current position, which is what you have here, right? But then no doubt your constraint was yi w xi plus b greater than equal to 1, right? Now that kind of constraint is kind of, it is still valid. I will say it is still valid right now for this point, red and blue, because it's still on the right side of this decision plane. But now we have started seeing some impurities within those decisions. Like some people now along that LOC and in that margin region. So now let's see what is the distance of that 0.1 from the line of defense of red. Well, let's call it as eta I, which is the distance. Eta I upon W is probably the distance of that point from this line, which basically means the equation of the line which crosses through that red point is -1 plus eta I, where eta I is strictly greater than 0. Right? And when eta I is equal to 0, you would touch this LOC. Because if you remember, this was -1 line after the equal sign. And this is the 0 line after the equal sign. And this is the +1 line at the top after the equal sign. So this is -1, minus 0.9, minus 0.8, right? And then is minus 0.1 and then 0, right? So you can see here that after that equal to sign, this quantity that I have here is going to be less than 1 on the negative side. Similarly, you can keep going and increasing the value after that equals and 0.1, 0.2, and ultimately +1. So you can see here that that blue line, which is within that margin, where is that sitting? Here. this would be less than 1 in the positive sense. It can be 0.1, 0.2, 0.3. That means all those points which are within that tube, they would have a new line which is -1 plus eta I if you are on the red family side, or 1 minus eta I if you are on the blue family side. Okay, so that means distance of any point on this line now, which is the red line, red point 1, right? You have this red point. Then again, use the same formula, put that line, you would have eta I upon W. So basically any point, distance of any point now would be eta I upon W. Just think of it like that. So if you are so this 1 upon W was the sweet value, right? Why? Because this is basically, what is this? This is this value, right? Only this part, 1 upon W. And this is the other 1 upon W. So we're basically saying, as far as your distances are concerned, a point is said to be within the margin if its eta I is less than 1, right? So look at this condition. For eta between 0 and 1, you are within the tube. That means point is between the margin and the correct side of hyperplane. This is margin violation. You have violated your own line of defense, but you are still within the same country or the same family. So we are calling it as margin violation, but you are still on the correct side of the hyperplane. The moment your eta is greater than 1, so look at this red point. I'm going to take this red point all along this line, right? So this one eta I was suppose minus 0.5 here, because it's growing, it's decreasing, right? It's decreasing and it's increasing in this order. Minus 0.9, so it's minus 0.5. This would be minus 0.1. The moment it touches this black line, you are sitting on that black line. And the moment it crosses that black line, your eta I has been greater than 1 from the red side family, right? So you can see that if your eta is greater than 1, point is misclassified. Because if eta is greater than 1, you have gone beyond this numerator, 1 upon W. So this was 1 upon W. And your distance of any red point is eta I by W. If eta I is greater than 1, you have crossed the boundary from either sides, making that journey. So that means the point is misclassified now. So just have that in mind, that eta I is basically measuring misclassification, right? If eta I happens to be greater than 1, then that point is misclassified. And if eta I is within that tube, it's a margin violation, but you are still correctly classifying it. Question. Let's go to raise hand first. Ram Mohan.
JD, I wanted to point out that I think eta corresponds to the margin lines, the red and blue lines, instead of the black line.
No, eta value is greater than equal to 0, right?
So the middle
eta
line,
equal to eta I equal to 0 is basically, so eta is basically what you are adding or subtracting from the constant on the right hand side of that equal to sign.
Yeah.
Right. So if eta is equal to 0. Whoa. Thank you. I understood.
Because you've also marked it on the graph.
Yeah. So eta I is equal to 0. Oh, I might have to read it. Eta I equal to 1. I think this is now fine, right? Yeah,
this is fine. So the black line is eta equal to 1.
Yeah, eta equal to
the safe lines, the dotted lines, the red and
yeah.
Oh,
I already had it. Oh, sorry. Yeah, I already had it written here in that discussion. Yeah. Eta equal to 0. So this. Oh, so this -1 minus 0.8 was the actual value after that equal to sign. After incorporating that eta. Yeah. So eta equal to 0 means it's this line, right? That's fine. And as you are increasing your eta, you're saying how far you are going from this line. That's why your eta is like increasing, right? 0.1, 0.2, 0.3. So it is 0, 0, 0.1, 0.2, 0.9, eta is 1, then 1.1, 1.2, 1.3, and this is probably 2. Because if you are exactly on the other line of defense, your eta high for this equation has to be
Yes, it is true.
so that you are sticking on this blue line now.
Yeah. So
Right.
it is 2 on when you. So anything greater than 1 is misclassification. 0 to 1 is not misclassification, but it is intruding into the margin.
Yeah. You are in the line of attack of either of the parties, right? So avoid that. Question now from the chat. Yeah, eta is the impurity. Yeah, because we want to minimize the number of misclassifications. So if eta is greater than 1, it's misclassified, right? So if we decrease the magnitude of eta, we are basically decreasing the number of impurities or number of cross-country movement, right? So misclassifications of points, right? Okay, but probably I think Ganga Jalandhar, probably this I might have corrected myself in the discussion. Probably that helps you. Eta equal to 0 is basically those margin lines. Okay, I think raise hand feature. Go ahead, Ashish.
My question is, like, am I getting this intuition right that eta is somehow giving us a width which is lesser than 2 upon mod of w, like Euclidean distance or like Euclidean metric of w, and like it's a smaller margin basically where we will just probably take out something which will contribute to the cost function, right?
So the intuition
Like,
here is
a little bit of easiness, like you can
yeah,
do
slack.
it, not slack. Yeah, it's like you cannot go beyond it, but even if you enter this smaller this smaller margin, still you will impose some
Yes,
cost, right? That is
yes.
something.
So we are saying we want to. So we are accepting errors now in our trade. So now we are accepting the fact that trailing error cannot be completely equal to 0, because we understand the fact that some points can cross that black line and it's still good. But then there can also be points from our own family which can be now beyond our line of defense. It can be within that tube between black line and the dotted line.
But
right?
it should not
So,
go beyond eta by w, right?
No, it can go. So no, that distance is eta I by w, but that value can also be crossing that. So see this one, the top point, 0.3. It has gone beyond 2 by w. So that is a misclassified point, right? But so we are going to penalize the model based on how many points you want to misclassify.
Basically, the loss for the points that will be higher than this eta by w margin will actually contribute to the maximum loss to the maximum. Yeah, sure. Yeah, thank you. Yeah, I got it. Yeah, thank you.
This is now the extra term. I'm going to add an extra penalty on C if C is equal to 0, capital C is equal to 0. That means if capital C is equal to 0, you're basically throwing away all that we had and you're back to hard margin. So for capital C equal to 0, what you want to do is, wait a minute, let me think of it. Capital C is equal to 0 means, yeah, I think this can play on a different scale.
Yeah, so capital
is inverse.
Yes, it's inverse. Yeah, so if capital C is equal to 0, then your classification doesn't matter. All you want to do is reduce W.
Right. So think of this, guys. You know, the best way I know.
Capital C is equal to infinity is hard margin.
Yeah, C equal to infinity. You know what, guys? We think of this as, this is the first time you are seeing that this is basically your objective loss, and what you had so far was basically your regularization. Think of it like this. This is like SVM turned everything on its head, where we started with the regularization term, and this loss was hidden in kind of the constraint. So you can see C as the weight you want to assign to the objective. In a way, C is inversely proportional to, you can say, as, so C is like how much weight do you want to assign to this loss. So if C is infinity, right? If C is infinity, that means your regularization term does not matter. And what have we learned? If our regularization term does not matter, then it means you are doing an overcomplicated model, which in this case is a hard margin classifier. So C equal to infinity is hard margin, because what it means is penalize every damn single point, excuse my choice of words, but penalize every point which might have misclassified, and penalize it so heavily, like C equal to infinity weight. That means anybody would now fear crossing the margin, because you're being so strict, you're so vigilant in that line that any small eta I which is positive, right? If eta I is slightly greater than 0, right, you're starting penalizing. That means what is eta equal to 0? This is eta equal to 0, line of defense. The moment you slightly cross your line of defense, even though you're in the same country or same family, you would be penalized heavily. So nobody would dare cross this point. That means it's a hard margin classifier, which we have been talking so far. If my C is 0, C is 0 means throw away everything that you have about data, because objective loss is all about data. That means you only have a regularization term, which is W square, which basically means you're underfitting, right? Which basically means you are learning a too simplistic a model if C equal to 0. That means misclassifications are allowed. Please keep crossing the boundary. Nobody is keeping an eye. That means the decision boundary would be taken for a toss. There will be no LOC, because you are now allowing points to cross each other's margin, and even going beyond the other countries or other lands into the other land, right? So that is bad as well, because you're too simple a model. That means you're not taking into account what the data distribution is. You want to avoid both these extremities. So you want to avoid C equal to infinity, which is strict, hard margin, because it has poor generalization. You want to avoid C equal to 0, because that would give you a kind of too simplistic a model, right? So this is what helps me understand. Even though C is a regularization parameter technically, but think of it as 1 upon lambda, where lambda might be the weight to this one in the previous discussions we had. So if C is too small, right, that means your weight your regularization term has a higher weight in this objective function, right? That means you are regularizing it well. Regularizing it means you are taking into some lenient or large margins. But if you take large C, right, large C, that means you are starting to getting strict on all these things, right? So you would want to restrict and be strict and make sure that nobody's crisscrossing your LOC. So your narrow margin. You take C equal to infinity, you're basically saying penalize every movement beyond that LOC. That means I would have a hard margin where there would be no single point in this tube. Too narrow.
The no man's land across the border, on both sides of the border.
Yeah, LOC. Yeah, that's the best example I could have come with. Today's lecture.
It's called no man's land.
Yeah, no man's land, right? So there you go. So here are some examples, right? This is C equal to infinity. You can see hard margin, too narrow, very strict. There is no point which is now in the no man's land. Everybody is respecting their guidelines. Now the issue is that while you have made sure that training error is 0, but it is a kind of overfitting it, because as we can see, there can be slightly a new test point might come in, which can be sitting quietly here as a point, and you might misclassify it as this one, right? So it would be a poor generalization on, or high validation errors that you would get. So you can see that training error is 0, and this is the value of margin. But now what we can do is we can have a softer margin with C equal to 10 and not infinity. And we can see this has now increased my width, right? That means I'm starting to get lenient. People can now start crossing their own LOC. There can be some people at no man's land. Now there is no now there are some people here. So you can see here that this point has quietly automatically crossed over. It has not technically crossed over. The margin has widened up so that it now is on the other side of that decision boundary. So there's a trade-off, right? Do you want to and see if C is equal to 0? If C is equal to 0, that means this margin is even widest possible. That means you're underfitting, right? So you don't want to too regularize it as well, right? So you can see here I've incurred a training error which is no longer 0, but you can see the margin has increased. Earlier the margin was 0.0966. Now my margin is slightly wider, 0.2665, but I'm now starting to introduce training error. That means 3.7% is fine as long as my validation error is better than the previous one. Okay, that was it. So that was all about soft margin classifier.
Is everyone convinced that decreasing W leads to increasing margin?
Oh, this formula, 2 upon.
No, just so this equation y times W transpose xi plus b, right? So you want to maximize the margin. So basically you want to maximize W transpose xi for the support vectors, which you can do by minimizing W so that x becomes further from the decision boundary.
Yeah. So we went over the fact that what this equation is basically telling you is you are well within you're on the correct side of that classifier.
Right.
Right. So that's what we discussed, right? So you like, if you are on that LOC, you want to be on that LOC or within your country.
Okay, great.
Right?
All right. Let's take some. Go ahead. Let's take some questions otherwise.
Yes.
Kasina.
Yes, sir. So in the same slide where we are saying yi multiplied by W transpose xi plus b is greater than or equal to 1 minus eta I, essentially, aren't we shifting our borders to the point one aren't we shifting our borders to the point 1 minus eta I and minus of 1 minus eta I on both the directions? Essentially, isn't that is what happened?
See, you are relaxing the constraint. Yes, from greater than equal to 1, you are now saying I'm going to take a kind of 1 minus eta I approach, where beyond that everything should be correctly classified, right?
Okay.
But what we are eventually learning is W. W is still at the same point. We are not shifting the W, but we are relaxing the constraint by adding that slack variable minus eta I, because 1 minus eta I would be like anything which is now, as you correctly said, is misclassification is allowed, right? So this point is minus 1 plus 0, right? So yeah, right? Minus 1 plus 0.1 minus 1 plus 0.5, right? So what you have here is you are trying to say that yi and this product, right? So where we have this product. Earlier, this product was this one, right?
Yeah.
Beyond one line. But now you are trying to shrink it and say, oh, it's beyond 1 minus eta I. I'm still good.
Yeah, that's so.
Right?
Yeah, got it. Fine.
Okay. So basically what happens is now we have started to have unknowingly, we have now created two constraints. One is the fact that your yi into W transpose x plus b. Now I'm calling it as f. So my yi f has to be greater than equal to 1 minus eta I. But there's another constraint that eta I has to be greater than equal to 0. So you can combine this into one loss function where eta I is either 0 or 1 minus yi fxi. So where is eta I equal to 0? Eta I is equal to 0 if you are on your own line of defense, like if you are in your own margins, dash lines. Your eta I would be equal to the second term if your yi fxi is greater than 1. no, if your yi fxi is less than 1, if your yi fxi is less than 1, then you are incurring some penalty, because what is yi fxi? So basically you're saying this, right? Let's go in here. So what I'm doing is I'm trying to take this, as we have done it before as well. We're going to take these two parameters into the objective function, right? This is what we have, right? So I will just keep it here on the slide so that you can read it. In the meantime, I will take some questions which I think I missed out. Ashish.
My question is that when C becomes equal to 0, right? Simply it becomes a perceptron model back again, right? Because anything can move forward. Like there is no respect of the boundary, right? Like crossing, like it basically there's no concept of margin anymore, right? Because there is no cost that moving between the margins is incurring, right?
Well,
Exactly. Go ahead.
not exactly.
Yeah.
Because there is a hard mark. So C equal to 0 means you are basically underfitting the model, but you're not respecting the data distribution. Perceptron was at least looking at the data and updating its weight, but in this case, it's not.
So basically what happens is that an SVM will fit a particular like WTX, the boundary line, and then after that it will compute all the margins. But after doing all that work, anything is allowed to violate that margin. So there is no point of construction of those margins, right?
No, so think of this C as a regularizer, right? Because if there was no extra term of loss function, you're basically learning a hard margin where you know beforehand your training error would be 0. So you're basically learning a model which is too strict, and your ultimate goal is to have 0 training error. What does this C and eta I tell you? It tells you that, hey, give me some slack. I can have some training error as long as I'm doing well on the validation. It's like cutting some slack, right? So in that case, you're still learning that, see, in both the cases, you have a margin. Now it depends, does your margin have any member within that tube, or are you allowed to have members in that tube and even crossing the border as long as you are doing good on generalization? That is the trade-off.
Yeah. And if you can just speak, like repeat again this max term, it would be great. Like this max term.
Okay.
Yeah. Thank you.
Okay, it's actually combining these two terms, right? It's basically combining these terms, because what you want to have is, what is your loss? Eta I is basically loss. Loss can be equal to 0, or it can be 1 minus yi fxi. That means either the loss would be positive or 0. When is the loss 0? When, that's what my next slide was talking about. Intuitively, my loss would be 0 if the second term is negative. That means yi fxi is greater than 1, right? That loss is 0. When is this condition hold? When yi fxi is greater than 1. When both of them share the same sign and are beyond the LOC line. If you remember, this is what it is. That's why I had this plot. I'm going to explain that max through this one. Right?
And this eta is like a parameter learned by the model, or is it like a hyperparameter?
The eta.
Yeah,
see,
eta,
there is no notion of eta in the objective now. See, where is eta?
Oh,
this is just
okay.
Eta
So
I is basically
something like a latent variable that was there just to formulate stuff, right? Yeah. Okay.
This is basically sigma eta I.
Yeah. Got it.
Yeah. Basically, the whole point is eta I calculates how many misclassifications are there in the data set. So see the regions which are yfx greater than 1. I have colored them here. When both of them share the same sign and you are well within your respective boundaries of your countries. That means if you're deep inside your country, you don't have to worry about anything. because your y(fx) is greater than 1. In that case, that maximum term is 0 comma some negative, because 1 minus greater than 1 would be negative. So you are incurring zero loss. That means if you are well within your country, deep down into your country, inside your land, you're not at the you're not going to get misclassified. What will happen if y(fx) is exactly equal to 1? Now, what is that line? Y(fx) equal to 1. Well, these are exactly these lines, the LOC lines of respective countries. If y(fx) is equal to 1, it means point is exactly on the margin, right? But again, there is no loss because they are still away from that decision plane, right? Because they are just at that critical juncture. Like a one step behind is safe, one step ahead is going into that no man's land. So you're still fine, y(fx) equal to 1. Hence, it will have no contribution to loss because that max term would again be 0. It would be 0 comma 0, which is 0, right? The problems start happening when you are starting to now go into that no man's land, where y times fx is less than 1. Now, y times fx less than 1, I have drawn it here. You can see the product, right? Y(fx) is less than 1 here. So point is violating the margin constraint and it will contribute to the loss, right? And then we are trying to accumulate all these margin violations. This can be margin violation. This can also be a kind of crossing the decision plane entirely, right? Because if you see here, as long as your this is interesting, very interesting, yi(fxi), you are now sitting here. That is one part of that third step. While you are sitting between 0 and 1, your magnitude is less than 1. That means you are in the right hand side of this LOC, but you are inside the margin. So I'm going to penalize you because you should not be there. So I'm going to penalize you. But now, what would happen if yi(fxi) is negative? If yi(fxi) is negative, you can see that 1 minus yi(fxi) is becoming greater than 1, right? Its magnitude is greater than 1. So you are trying to now cross. You're now starting to cross this decision boundary, even if you are a red sample. Right? Remember this red point at the top, eta I, it is greater than 2. So if this is minus 1, if yi(fxi) is equal to minus 1, right? That means you have come to the step of 1 minus 1 is 2. That means your distance from this plane is now 2 upon w, right? That means the moment you have crossed less than 0, you are in violation. So basically, it's a good measure. Why? Because as you are moving farther from your own margin, as you are moving into other people's territory and away from your own country and own line of defense, you need to be penalized more and more. That means the amount of penalty that has to be assigned to you should increase as you move further from that margin. And that is what is happening, because as you sit, as if a red dot sits on the blue line, if the red dot sits on this blue line, you can clearly see that this loss would be 1 minus 1, which is 2. Yeah, because for this point, this one is minus 1 here, right? And as you keep increasing, this loss would be 3, 4, 5. So basically, this is what we have. This is called a hinge loss. The maximum 0, this is called a hinge loss. So this red line, which I have now crisscrossed by different sections, is what my hinge loss is all about. As far as you are on this vertical line, let me now shade it so that you understand. Look at this line where your, so this x axis is this yi/fxi, and this is too much, right? I'm just saying it verbally because I understand. I have spent a lot of time yesterday doing this. For you, it might sound okay, like chalta hai, samajh mein aa raha hai, it's okay. But once you go back and do this, right, so you will be able to convince yourself more. It's always like that. So what is this is in this line yi/fxi, right? So in this case, you can see that this is basically my loss, eta I. I'm finding how much error I'm doing. So if my yi/fxi is greater than 1, right? This is that these circle points, just keep an eye on this one, right? If I'm greater than 1, that means I'm along this axis. So I'm on the correct side of the individual margins. That means I'm well within my country, right? Within my country. That means I'm not going to contribute to any loss because I'm very far away from the decision plane to influence the decision plane, right? So I'm correctly classified. Now this slope, okay, just be careful what this line is. This is maximum of 0,1 minus yi/fxi. This is what this line is, this L shape, angular L, right? So I'm here within margin. If you see this within margin, what is my yi/fxi? It is between 0 and 1. That's what I told you, right? If y/fx is still positive, but its magnitude is now less than 1, that means you are now in your correct side of the decision plane, but you have now ventured into the no man's land. So you will start to get penalized, because I was hoping that nobody should dare move into that space. So I'm going to penalize and let the model minimize this loss, right? So I'm going to accumulate my loss. So that loss would be now 1 minus yi/fxi, right? 1 minus yi/fxi. That's any point here. As you move in the negative space, which is y/fx, the x-axis, have you moved to the negative space? See what has happened. This was the line. This was the point for this one, right?
Jyoti, that's a black line.
Yeah, that's the black line. Yeah.
Yeah.
Yeah. And these lines, this inflection line, are the respective red and blue line. I think I have labeled it correctly, so let me not add more things on my diagram, otherwise you will get confused. And as you move negative to 0, you have crossed that exact LOC, which is my black line. Hence, your loss, you have started to misclassify. You can see this region, which is the misclassification region, where the x-axis is y/fx, which is all negative. So this is a kind of a good loss function. Why? Because as you're moving farther, as you're moving away from your own lines, right? So this is your own line. You had to be, this is what you wanted to have. You wanted to be on this side. But now because of some slack, you are allowed to be here. Hence, you're accumulating those errors. First of all, you will enter the margin, because if you are a point here, you will first enter the margin. That means you will go from this to this side, and then you will start violating it if you are still going along. So you will reach this space. So as you are moving farther away from your own space into the other country's land, then your amount of error would start increasing this way. This is the direction of increase in error, which is a measure of distance, right? So as you can see here, this gray dashed line was basically misclassified points as labeled here. Red has ventured into the blue space, blue has ventured into the red space. This green dashed line is within the margin. That means blue is still within its family, but it's now inside the tube. Red is inside the tube, so they can now face attack, right? And if you are a pink dashed line, well, you are safe. You can see the pink points are safe. There is another loss called as 0-1 loss, right? Where you say that if you have which basically means if you have misclassified, that means if your y/fx is negative. See, y/fx is negative. means they have opposite sign. Your prediction has an opposite sign to your actual label. That means you are assigning a constant loss 1. So that is why it's not a great measure compared to hinge loss, because at least hinge loss is penalizing proportional to how much far you are moving from your territory into other man's territory. Whereas a 0-1 loss is assigning a constant loss 1 for misclassification, right? So that's why we stick to hinge loss, and that has its own benefits. So it's a kind of a better approximation of 0-1 loss where you penalize based on all these things. This is again a quick recap. Okay, so I'm going to take a pause, not speak for 2 minutes, let you gather your thoughts while you read this. This is just a summary. And probably let's take questions, and we have hit the 2 hours mark. So I will let Dr. Sethi decide what we have to do. But then let me see how much we have optimization. So I think it would be a stretch goal to go over kernel methods. We can still quickly go over this one because it's down optimizing it. But yes, kernel methods now might be a stretch goal. Let's see. Okay, we can take kernel methods tomorrow as well. But again, this is important. So in summary, I have mentioned my observations here. Convince yourself if this makes sense or not. Let's take some questions.
One question is, what are the hyperparameters we need to tune in SVM?
Actually,
C is one of them.
C is one of them because
So this is called this is called a linear SVM. So in linear SVM, it is basically just C.
Yeah, you can see the 2 examples here. They were trying to optimize it so that they have good generalization, and they eventually found out that C equal to 10 might be a good generalized model, right? So C is there.
When we go to kernelize SVM, we will have C and some kernel hyperparameter as well.
Gamma.
Yeah, like a bit of the kernel or something.
But I was curious, Dr. Sethi, like, where is my C? Oh, there's a C. I completely forgot that there's a parameter. Oh, yeah. There's your C. There's a hyperparameter. Right, great.
The trade-off between leniency between hard margin and soft margin.
Yeah. Do you want to have a strict teacher or a lenient teacher? Depends on C. If C is infinity, you have a very strict teacher.
Yeah.
Questions. Let's take more questions.
There's nothing on YouTube. Yeah.
Nothing on YouTube. Nothing on raise hand. Great. Everybody is there, right? I will share these notes so that you can read. I've just summarized what I had. So basically, what we have is now.
Jyoti, should we take this tomorrow?
I can quickly go over this. It's nothing much.
Okay.
This is nothing much. I'm going to stop before kernel methods.
Okay.
See, now what has happened, folks? We have W square, right? And I have this. This is a quadratic curvature. And then the hinge loss, I'm adding these 2, right? I'm adding 2 optimization goals in one form. So there's a property that now both of them are convex functions. Why is hinge loss? This is the hinge loss graph, right? Why is this? If you remember a convex function, if you draw any line, it is well within this plot, right? So it's a convex function. So now what has happened is if you add 2 convex functions, right, it might or might not be a convex function, right? A non-negative sum of convex function. Oh, it is a convex function. Oh.
Yeah, as long as they are added with a positive multiplication. Yeah.
Yeah, positive. Yeah, non-negative sum, right?
Yeah,
that is a. And if you remember, folks, your C was positive. Right, this was a constant C, which is the penalty. It is positive. C is greater than 0. So in that case, it would be positive, right? So just discard this. I don't know why that's so positive, right? That's what it was, right? Just look into this one. Loss, regularization, convex. If it's a convex, you can use your gradient descent, and you know that the local minima would be a global minima, right? So there was one way of doing it using a QP solver. The other way is you can do it using gradient descent. Again, you can slowly approach that sweet spot. So again, it's written down here, right? Again, this is the minimizing that This is that function that we have here, right? And there can be some change of, see, now they have created this change of variable. Now it is back to the good old lambda, which we have been following so far. So if my C is infinity, my lambda was 0. That means it was a overfitting model, because lambda equal to 0 means no W square. So it's hard fitting. If C was 0, lambda would be infinite. That means regularize it as much as you can. That means you are doing underfitting. No record of data in the optimization. So now, because hinge loss is not differentiable, because you have this sharp point, right? So we do a subgradient method where we solve on either sides of it. 1 minus y fx, and this is constant 0, right? If you take the subgradients, this is what we have, because there are two parts of this equation now, right? And now you can solve it using subgradient method, which is here. It's again nothing fancy. Wt plus 1 is Wt minus eta delta j, right? This C or JW, what you can call, what we have been learning. So there are now two parts of this update. If your y fx is less than 1, which means in this line, right, this is y fx 0, or this was y fx, where was y fx 1? Oh, yeah, this was 1, right? This is y fx, and this was my error. Remember, as I went beyond this one, I started incurring penalty, right? So in that case, I'm going to subtract the gradient, right? Which was this one, minus yixi, right? From lambda wt, which comes up from this equation if you differentiate the regularization term. But if you are not misclassifying anything, right? That means you are on the correct side of the points. They are not going to contribute to your update, right? So in that case, you're not going to remove any term. You're just going to do this update, right? So it's independent of the data. So in a way, this is the first point where you are seeing that if you are well within your country, right? If you're well within that, if you're respecting your own margins and you are well within your country, then you should not be influencing your data should not be influencing the update in W, because you can see in the second one, there is no information about XI. And that is the whole idea, because ultimately those XIs would be chosen who are going to decide how my structure of that hyperplane is going to be, where is it going to lie. And those XIs would probably either be support vectors, right? Or see, this is the contribution of the loss, because these points have started interfering in the margin and going cross it, right? So if your y fx is greater than equal to 1, that means if they are support vectors or if they are within your family, they are not going to affect your update. So that means your entire readjustment of W or the hyperplane, W is a normal to the plane, right? So entire adjustment of your hyperplane is now getting fine-tuned by all these points which are trying to interfere and come into the margin or misclassify, right? So that's what it is. I'm going to end it there. There are other SVM solvers which exist in libSVM and where they have different ways of implementing it. But this was all about soft margin SVM classifier for linearly separable data set. There can be some points here and there, but we are still going to learn a linear model. So ultimately, I'm going to learn a linear model, even if I have some points crisscrossing into each other's place, right? So my decision is still a linear. And tomorrow, before tutorial, I think I can go over the kernel methods, right? But I'm going to release the slides so that please read ahead. It's not that difficult, but yeah. Any questions? Thank you so much, guys. If you don't have questions, feel free to leave. It was a good session and hope you could understand it. We'll see tomorrow and finish this topic. Questions? C is the hyper. Okay, Amit Sethi answer. Any other questions? Feel free to raise hand or unmute and ask. YouTube, keep an eye. Yeah, Ram Mohan, go ahead.
So I'm trying to understand. Let's say, so to summarize everything, this is like an overview question. Let's say we are given a data set. We have a couple of positive points, couple of negative points. In my imagination, in my understanding, what I'm trying to think is, first we find the two nearest points, which are support vectors in this case. Then we draw a line with those 2 points for each classes. So those will be my 2 initial parallel lines, which will be a margin. Then I try to maximize the 2D part and find a middle line, which basically divides the whole thing into 2. And this is how this was the first initial case. Is this right, or am I going wrong somewhere?
So you're trying to summarize what you went over, right?
Yeah, what I understood basically.
Yeah. So we have this. Were you asking about the test? Like, how do you test a point, or was that a separate question?
So that's basically, so even the training part, like first what I'm trying to, like, given a data set, right now it is testing, training.
Okay. Given a data set, we have
2 clusters of points, positive and negative.
Oh, hopefully, yeah. In a training set, it is given to you. It's a supervised learning, right? Yes. Go ahead.
So we have 2 clusters, positive and negatives.
Let's call it 2 classes. Don't mix clusters here because that has a different interpretation.
Yeah.
2 classes. Yes.
Classes of points, positive and negatives. What my first step is basically find the 2 support vectors for each class. I'm taking this for an example that both of them have 2 support vectors. There can be 2, 1 or 1, 1. That's okay. But right now in what we discussed, we had 2 support vectors for each class.
Okay.
So I find these 2 support vectors. I get a line for each class with those 2 support vectors. These are my 2 parallel lines, which are margins basically. Then I'm trying to find a middle line, which is noted by W transpose X plus B equal to 0.
Okay.
And this I find by maximizing the distance between the margins, that is 2D.
Yes.
That's basically the first basic SVM that I have. That's the hard.
That's the intuition, not mathematically though, but it's an intuition. Mathematically, you're learning the W directly. You're not learning the support vectors first. In the primal form, you get information of W, right? Okay. But that derivation, that optimization form actually came from that inspiration that there are some points which are called support vectors on which this hyperplane would rest. So that intuition is right, but remember that I talked about there are 2 ways of modeling SVM. One is a primal form, which is in terms of W. There is a dual form, which is in terms of, you can think of it as importance of a point as a support vector. So very quickly, there is another form which is called dual problem to this, where instead of W, we minimize it over some alpha, where alpha, you can think of it as importance of every point to the hyperplane. That means if alpha is equal to 0, they do not influence my hyperplane. And for support vectors, alpha would be non-zero, positive, right? We'll learn more about it in the next class, but the idea is you are, intuition is right, but don't think that my first job is to actually find the support vectors, because that would be the problem of the dual formulation.
Okay, so this what we learned is basically a feeling or intuition of this, and the way we code it is going to be different.
Exactly. So they are all interrelated. Maximizing the margin is same as finding those support vectors for that decision plane, right? So while this was all about maximizing the margin, right, this dual form, which we're going to learn when we're doing kernel methods, is basically finding those support vectors. And what this support vectors means is, like, if you discard all the training samples and just keep the support vectors, you can get that hyperplane. That means to create that hyperplane, the points which are well within your own respective countries have no influence on creating that hyperplane. So the whole idea is to find those selected support vectors, which you can keep within yourself. And then with that, you can create the hyperplane.
Yeah. One more thing. This was the first basic, the first hard classifier that we had. Then if we go for the slack thing, then what we're trying to say is, like, initially we did not have anything. The hard condition was we did not have anything between the margins, no points in the margin at training time, right?
No points within the margin and no points on the other side of the territory as well.
No misclassifications.
No misclassification and no margin violation. That was hard margin.
Yeah. So in the slack thing, what we want to do is we want to give some slack to the points that are within the margin, and we want to give high error on the misclassifications, right?
No, we want to penalize every single point which tries to violate your own line of defense. We had this line, right? Any point which is within this tube or crosses over this tube from respective side, I'm going to assign a distance, a loss measure, which is proportional to the distance from their own line of defense, from the defense, right? So if you are within the tube, well, you are not that too far. If you are within the LOC and your line of defense, you are still within your country, but you have started venturing into no man's land.
Yeah,
so
I got that. Yeah, I got that.
But as you move away, you increase your contribution to loss.
Yeah. What I'm trying to understand is, like, by adding that C and that error term, we are basically trying to find a different boundary that was classifying, like.
No. What we're trying to say here is, if you're saying compared to hard margin, we're now trying to relax that constraint and probably might learn a wider margin by allowing some points to misclassify. So now, because of this term on my right hand side, my training error might not be exactly equal to 0, but I'm going to optimize this problem so that at least I can ensure this contribution of error is as low as possible. So it's a trade-off. Do you want to strictly make this term not contribute to any error, or do you want to take some violations and make sure to reduce the impact of those violations? Understand? So we are trying to say that rather than learning a very narrow tube, we are going to learn a wider tube. And we do understand that by increasing the margin and by learning a larger margin, we might now have some points which can start violating the margins or violating the decision boundary. But that is fine with me because I have optimized it in my objective function over this, right? It's a trade-off.
Okay.
So that's why my training error will not be 0, because see, you are in a narrow space. As you increase more and more space, more points would start coming in, right?
I got that. So
go ahead.
What I'm trying to understand is, do we, in any case, am I changing the boundary, the middle line, the fx equal to 0? That line, is it?
Oh, no. That line is still fixed, right? That line is still. So that line is basically saying, okay, let's say you have plus. Let's go to that example of C, right? Where we had, I think we might be
changing the margin. That I understand, but I'm asking, in any case, do I change that line?
Yeah, it's changing. See, it's 0.2. This line was 0.2, right? Because as your margin change, as your width increases, right? As your width increases, see, this line is also changing. Yeah, because you're trying to fit your model. Because as your planes adjust, see, as these earlier, this plane was going over this point, which was the closest point which was the closest point nearest to the other country, right?
Yeah.
But now you can see that point is still here, which is 0.2, 0 minus 0.4 is the same point. But now this entire support has moved to this, which you see here.
Yeah.
So as the candidates change, see, it's like a game. You have 5 people standing here which are going to decide the support vector. Now, do you want to include this in that army of defense? If yes, then your line of defense would change. So
Got
based on which candidate points you choose, your line of defense would change, because that's where you're drawing the perimeter of your country.
Got it. Got it.
Right?
Could you,
Like,
last thing, go to the loss function, in which we include the error term.
this one?
Yeah. Could you explain just this, the adding the error part? Could you explain it again, please? Like,
so it's basically, what was eta I? Eta I was how much distance you are traveling from your own boundary. What is this distance of red point? Eta I upon W.
Yeah.
What is the distance of this red point, which has ventured into that blue man zone? Eta I upon W, right? So basically, eta I is the measure. That's why eta I comes up on the right hand side of this equation, because when you find the distance of this point from here, so it would be like B and B gets cancelled, right? And then eta I gets added up, right? If you want to look here, let's say -1 plus eta I. So this was B plus 1 minus eta I, right? Equal to 0.
Yeah.
W transpose X plus this, right? Now when you subtract it from this line, right? What is this line? W transpose X plus beta plus 1 equal to 0.
yeah.
Right? Now what is the distance between these 2 points? You're going to subtract the constant terms. B plus 1 minus eta I minus B minus 1. These cancel. Magnitude divided by norm of W, which is eta I by norm of W.
Yes.
This is the distance of that point, right? So so that means I'm going to sum over all these violations, eta I, because every point which is now within the tube or has crossed to the other country, it would have an error which is proportional to the distance from its own line of defense, which is eta I, right? If eta I is greater than equal to 0, then I can be sure that I can do summation of eta I. So I'm basically adding all these losses. Eta I is basically how much I have traveled far from my line of defense, and that is proportional to the loss I'm going to do. See, this was the hinge loss, right? Your hinge loss, your loss is proportional to how much you have ventured into, how much far you have gone into other side. So see, this is increasing. So all this is eta I. So you're going to sum up. So any point you find on this slant line, any point which makes you go on this side, that means you are on this slant line. So you're going to add those up.
Yeah.
Right? So you're going to add all those eta I's. That's my sigma eta I. Understood? So
yeah,
you're going to add the contribution of losses. That's because that's the contribution of that point to the loss. Just take time and go over the slides again. Think of eta I as contribution of a point. So eta I 1 to n. Not all points would have eta I as non-zero. If you are well within your boundaries, eta I would be 0 for all those points. The moment you start violating your LOCs, then your eta I would be non-zero. And then you want to sum up all these respective eta I's. And that's what it is, right? That's what it is. You're summing up the losses.
All right. Thank you, JD. Thank you so much.
Any more questions?
Yes, JD. So, see, let us go chronologically. First, we have our training data, right? For suppose we are given a training data and we want to apply the SVM classifier. Okay. So, what are we essentially doing in the chronological order is that first, taking the data, we want to fit a decision plane, which is W transpose Xi plus B, correct? For each data point.
Fit a line.
I mean to say W transpose Xi plus B, like we are seeing, I mean, with respect to W transpose Xi plus B equal to 0, we are seeing where our point is. And with respect to that, we want to minimize the cost function. Could you go to the cost function slide, please?
Yeah, sure. Give me a moment. Okay, so loss function, right? Where is
No, no,
the
cost function. Cost. It's better.
here?
Oh
Is
yeah,
this
this one.
you see all the cost functions here?
This one. Yeah. So here, what we're doing is for every point, we are plugging in xi and the decision yi, and we for all the points we are summing it over.
Jyoti, I can take the question. Can you repeat the question, Kasim?
Sir, what I meant to say is, for suppose we are given the training data, okay, with the
Okay.
labels yi, to which class it belongs, okay.
Yeah.
So what I'm essentially asking is, how are we proceeding with the model? For suppose in linear regression, we plug it in, we adjust the line, and like our measure is the mean squared error. With respect to the mean squared error, we want to decrease the mean squared error. Like that, how are we going chronologically here? That's what.
Yeah. So you have all the points which are in, let's say, some n-dimensional space, right?
Okay.
D-dimensional space, sorry, D-dimensional space. So your X has D dimensions. And in this picture, we can only show 2 dimensions. So we are showing X1 and X2.
Okay.
Okay, so X1 dimension and X2 dimension. So all your points are now scattered in this in 2-dimensional space or D-dimensional space. Now you are coloring the points blue or red, training points alone, blue or red, depending on whether they have +1 or -1 label.
Yes.
Okay. Now you are randomly initializing some W and B. So it will give you some black line.
Yes.
Okay. So that black line has some loss, which is W mod of W squared plus C max of 0 of 1 minus yi fxi.
Yes.
What is fxi? Fxi is defined exactly by W and B.
Okay. Yes.
Fxi is nothing but W transpose X plus B.
Yes.
Okay. So
Yeah.
W is built into this F that you see in the loss function.
Yes. Yes. Got it.
Okay. So both terms in the loss function have W. Now, if I change W or if I change B, this loss function will change. The value of the loss function will change, summed over all training points I to n. I is equal to 1 to n.
Yes.
Okay. So I can always choose a W and B such that this loss is minimized.
Yeah.
Which was exactly what I was doing for linear regression when the loss was MSC.
Yes.
Right?
So
It was MSC plus lambda times W squared. Instead of lambda, we have the inverse of lambda, which is C, which is on the other side. Okay.
So initially we have randomly initialized W and P, and after the entire process is done, we get this optimized line, which is exactly bisecting both our borders, correct?
No, it depends on value of C. If your C is infinity, then you will get this.
No, even if it is the relaxed one, the black line which is there, W transpose X plus B equal to 0, in the slide we are seeing, that is obtained at the end, right? After all this optimization.
Yes, you are right. Yeah. So for a particular value of C, you will get a particular black line as the optimized value.
Yeah. Okay.
For a different value of C, you will get a different black line.
Yeah.
See this example,
Yeah.
So here C was infinity, hard margin, nobody was allowed inside that tube. But if I relax my C, you can see that my decision boundary has changed. And now this 1 point, I'm okay with misclassification as long as I have a good generalization now. Because that point I'm an outlier, right? So I'm not fitting the size.
Hello, sir.
Questions? Yeah.
Hello, Amit sir. So we are trying to minimize the perpendicular distance from all the point with this first black line. Then after that, we tune that. Is that?
Okay.
Not minimize, maximize.
Maximize the margin. Maximizing margin.
We don't want points closer to the black line. Yeah. We want them to be far away from the black line.
Oh, okay.
Okay. So how do you maximize? So look at this constraint. W transpose X plus B is greater than 0, greater than 1.
Yes, sir.
Okay, look at it carefully. How do you ensure that? You either increase X, which means you take X away from the margin, or if you are fixing the X to be equal to or the scaled X to be equal to 1 for the support vectors, then you can maximize it by decreasing W, because the W and X are being multiplied.
Correct. Yeah. Yeah.
Okay, so they work in inverse of each other in some sense.
Yes. 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 So we have to increase the distance, right?
Yes.
Correct.
So if you decrease W, then the only way you can ensure that this entire thing is greater than 1 is if W transpose X is very large. That means it is away from the margin. W transpose X plus B.
Yeah. Yeah. For every point here. Correct.
Yes.
Yeah.
Yeah,
Thank you, sir.
Satyajit, you can think of it as if we had a very narrow margin, right? Then any point, anyone can just run across and quickly jump over the decision plane, right? If we had a
Yes.
very narrow margin, कोई यहाँ से भाग कर आएगा ना, कोई, like if you're running across this, you will quickly go on to the other side. That's why you want to give some space where
Hmm.
even if you by mistake cross it,
Yes, sir.
you're still on the right hand side
Okay.
of the decision.
Yeah, one last question. So how can we find out the performance of this SVM? I mean, what I'm thinking means this, can we use true positive and true negative here?
हाँ,
And
मतलब
false,
it's like W transpose X
this is
plus
true positive.
right?
Yeah.
No, this is X test, right? So from 1 to all the test samples, you calculate this, you calculate the error, right? So you predict it, validation, right? So you have the y true labels minus the predicted labels, and you find your measure, right? So in that case, you can find out how many true positives you have, how many true negatives you have. Plot an ROC plot. Have we taught them ROC plot?
Yes, sir. That is
Yeah.
okay.
So in ROC you can get the good value of C, right? The hyperparameter. So in ROC it's like true positive and false negative, right? So in something, if plots are like this, then the ones which are at the bottom the top left, if there is a kind of ROC plot, then that point is basically the good hyperparameter for which you have high accuracy.
So we can use here. Thank you.
Yeah. Always use ROC if you have hyperparameters.
Yeah. Thank you, sir.
Any other questions? I think the chat, the raise hands have been done. I don't see anything on the chat. YouTube, I'm not sure if you have on YouTube. Okay. Then.
There are some questions on YouTube.
Yes.
Manish Apte is asking, can you explain what is hinge loss? And then Priya Ranjan is asking, can you explain the by chance case to cross the margin? I didn't understand. So I think what he means is, yeah, let's talk about the hinge loss.
So hinge loss is nothing fancy. It just popped in on this slide. Why? Because if you see, this is what we had, right? We wanted to make sure that we are correctly classifying the data points given some slack eta I. Now, when I introduced this slack term, I had to make sure that eta I is greater than equal to 0. So now, basically, I'm trying to optimize this function, but given two constraints. First of all, you have to make sure that points are respecting their own land with some slack variable eta I, and also eta is greater than equal to 0. So I'm trying to create a constraint which captures these 2 points, right? This is what it is. I want to capture these two constraints into one. So what it basically means is, look into this one. You can rearrange this as eta I is less than equal to 1 minus yi fxi, right? And eta I is greater than equal to 0 from the second one, right? So now what you have to Oh, no. I think I am mixing something here. Here eta I is greater than equal to 1 minus yfx, and eta I is greater than equal to 0. So these are the two competing constraints, right? Now what to choose when? So, well, that depends on the value of yfx. If you're already within your respective boundary of yfx, right? See this point. If you're well within your boundaries, then yfx is strictly positive, strictly greater than 1, right? So in that case, this equation would be eta I is greater than equal to, suppose, 1 minus some positive value, which is greater than 1, right? So 1 minus 3, let's say 3. So this is eta I is greater than equal to minus 2. But then you have another equation, which is eta I is greater than equal to 0. So intersection of these two constraints is greater than equal to 0. Hence, you have to take one of those two depending on which one is maximum, right? So either it is 0, when it will be 0, when this term is greater than 1, right? If this term is not greater than 1, that means there has to be now some contribution to loss. Because if this was greater than 1, if this term is greater than 1, there is practically no loss associated with it. That's what eta equal to 0 means. But if yfx is less than 1, which brings me to this plot, right? If yfx is less than 1, then you will start adding all your errors. Hence, this is called as hinge loss. This curve is called as hinge loss, this plot, right? Hopefully that answers your query. It's kind of a loss function. So as I mentioned here, in regression, we took MSE. In SVM, this is called as hinge loss. So we are going to minimize the hinge loss. If you can get me 0 hinge loss, great. But practical purposes, it's not possible. So we take some training error and optimize it over a more generalizable function. Can we use some other loss than hinge loss? Well, for SVM, we stick to this because this is coming from geometry of SVM, right? If you see the difference between all the classifiers, linear regression to MSE, right? For logistic regression, it was the loss was associated with the probability, right? How much you want to classify, maximizing the log likelihood or minimizing the cross entropy loss. So basically, the nature of this loss decides what kind of model it is. So this hinge loss came from the geometry of SVM. Like, how do you want to understand, right? So this was all for SVM, hinge loss. If you change the loss, it will no longer be SVM. Question?
So can you explain a bit about gradient descent update? There should not be any update if the classifier is
so it is
correctly. So there should not be any update while correct.
Yeah, because of this part, right?
But you
because of this part. This is a constant 0 because your function is 0, 1 minus y fx. Or let me write it as w transpose x plus b. This is my function. It's not differentiable at this point. So either it's strictly 0 on the right, or it has a linear dependence on this yfx. So what are these points? These points which have 0 loss. This is a plot of loss, right? So this means all these shaded yellow highlighted ones have 0 loss. Now, which points have zero loss? Which are well within your margins, well beyond your margins. That means we are well within your country. So they should not their value, their features, that data features should not contribute to W. Because the whole idea is to be selective. Your hyperplane decide is only dependent on the points which are allowed to, which are in the verge of getting misclassified, or which are violating those conditions. That's what your loss is defined as, right? So all this loss, all the points which are on this line, linear line, these are all those candidate points for whom y(fx) is less than 1. That means it includes points which are within the margins or which are starting to go beyond their own line into the other territories. So we want to accumulate those losses. So hence the contribution of those features. So those data features are important. See, in this equation, it is independent of those points which are well within your country. That means for all practical purposes, you could have made this as a more density on this. They would not have influenced your decision plane. But a small dot here, red dot here, it would start impacting my surface W, because that's where my support vectors lie. It's like 5-6 people are holding that line of defense. If you add more and more people in that line of defense, they start adjusting based on their value. You have one army person who is strong fighter. If he joins your line of defense, your quality of your line of defense increases or decreases based on the quality of that army person who joins your line of defense. If you are a civilian, you can have millions of civilians sitting far away from that boundary. Their skill set is not going to affect how you want to have that line of defense, how strong or bad that line of defense is. If you can understand from this example, that's what it basically means. Your civilians have no influence on how strong your line of defense is. But if you add more and more army personnel from your own country into that line of defense, every army personnel skill set makes sure how strong that line of defense is. Also, if somebody from other countries' army, or if any other country's army or civilian comes into your own line of defense, that will also create a reaction on your side, right? So that those kind of reactions that you have to these army people coming from those other side, or civilians illegally crossing that border, that would have an influence on how strict you want to be or how strong you want to be in your line of defense. So
first update is very much clear. What I am asking is the second update, the minus term.
This is not the second update. This is not the second update. This is either this or that. This is the civilian. This is the civilian who does not have any effect. Do you see any data point X in this equation?
No
so
data point.
X is that strength of that civilian. So your W is not getting updated by the strength of that civilian, because it does not matter.
Okay, fine.
But
only
here is the
thing that matters.
point. Yeah, point
There is
of
no
point.
update. Okay.
Yeah, no, there is an update, but the quality of that civilian doesn't matter.
Okay.
See, what is that update? Update is just a scalar multiple of n lambda. So it basically means the normal vector stays as where it is, but it is just scaled, right? So your plane does not change, but your scaling parameter changes. So your line is still sitting there, which is true, right? If you as a civilian join the army with no skill set, then are you going to influence the decision boundary? No, right? If you don't have any skill set. That's the same thing.
Fine.
How do we calculate? Let me go. Okay, Manas. Yes, yeah, I was thinking changing the linear product loss to a. Oh, yeah. For all those things, you can take a square term and all those things, just like L1, L2, and all those things you can do, square loss and all those things. How do we calculate feature importance in SVM? Feature importance is separate from data sample importance. So feature importance means you have 5-7 features, right? I think for feature importance, lasso is something that is good at selecting your feature. In this case, the weights W are basically going to see in linear models, W are basically telling you how important that feature is. That is the beauty of linear models. It's just like your GPA, right? Weighted score of all your GPAs in individual subjects. So if you have 10 features, then their weights basically tell you which features are more important or not. But that's what it is. But if you were concerned about data importance, because here important data points are the points which are called as support vectors, or the points which are crisscrossing the margin. So that importance of data, which decides the nature of plane, we will talk about it tomorrow when we learn about support vectors and how, that's what I was briefly saying. The dual problem is all about that, finding the importance of the data sample being a civilian or a support vector or an intruding point. Hrithik, based on SVM coefficient, yeah, if you meant SVM coefficient meant W, yes. Aryan, I meant to say like we have a quality that is more evident than others. No, quality as in what? Accuracy? Do we have a quality measure of if SVM is a better model than any other linear classifier? Aryan, can you just unmute and ask? I think that would be much better for us in the interest of time as well. Satyajit
Hello?
in SG. Yeah, yes, Aryan.
Yeah, I was saying that suppose we are classifying a flower and we have various features for that, and from we somehow find out that it is the classification is basically depending on some features more than the rest of the features. Then what do we do in case of SVM?
If when you found out the decision plane, you found out the W's, right? Now that W's is basically telling you how important of one of the D features of the data sample are, right?
Right.
So after like if there is some W which is very small, 0 point something, and this is all taken into consideration after you have normalized the feature and the data set. After that, if you find some W small and large, that means you can so in linear models it's interpretable, right? Because in linear models you can put this list of W and find and tell your customer which features are important and not. In terms of right. So size of the leaf can be an important feature than color, probably. Yeah.
Okay, thank you.
Sure. Satyajit, in SGD the loss is calculated, the weights are calculated as it is inside for loop. Oh, I think yeah, the loss.
Sir,
the loss is calculated.
Sir, actually, this is one quiz question, sir. So there it was written that the weights are actually updated after the loss function at once, or it is immediately. So as per the
So SGD is online. SGD is online. You update W for every test sample as it is. Whereas in batch gradient descent, you wait until you get the contributions from all the million data points and then do the first update W.
Yeah. So in the quiz, sir, it was written in gradient descent only. It was not mentioned. So it was the correct answer was at once we will update. But I think it is updating.
So no, when it said gradient when we say gradient descent by default, it means batch gradient descent. If that is what it meant, then the answer might be correct, right? So if we mean SGD, we will say SGD. But by default, gradient descent means the standard gradient descent, which is batch gradient descent.
Okay, fine. Okay.
Right? SGD, we will specify SGD. Mini batch SGD, we will specify mini batch SGD. GD simply means batch.
Okay, gradient descent means batch only. Okay, fine. Yeah,
it's like a monomer, because you can say, oh, I'm using gradient descent in deep learning, but practically you are using mini batch SGD, but the core principle is GD. But yeah, whenever you see GD, it's better to take it as batch first and then ask clarifications, right?
Okay, sir. Yeah, got it.
Yeah.
Sir. Thank you.
Thank you. All right, guys, we have made it a record, 3 hours. Okay, go and sleep. We'll meet tomorrow. Any questions, posted on campus wire. Dr. Sedi, I'll see you tomorrow. Take care. Good night. Aryan, welcome. Take care. Bye.